Yeah, I'm sorry, I know this is disruptive. I just want to, we got just a couple of things to do probably in class early today. I just want you to think about that, the class review that you just filled out, especially because I want to take your picture. All right, now, if you have a warrant, get out, because I'm going to post this on the web, all right? So if you don't want it on the web, you need to run. Okay, let me get a couple. I don't know how to pan around this. I think it's how to do that.
This is up until
Let me do one more because I didn't have a choice for everybody.
I don't want to be like
There we go. All right. I'll put that together at some point.
yeah.
All right. So good luck on me.
Lucky guy.
The doors. All right, everyone. I know you're all excitable, so just got to get through this hour, all right? Class business, let's see. Well, you got a little bit of a better education than this, right? This is the end of someone's class. That's anyway. Okay, class business, I got your last homework, and obviously I never posted another problem set because, I mean, those phase diagrams, there's nothing to ask questions on. We're going to continue with symmetry stuff today. It may fall a little flat. For one, I've never taught this before. For number two, normally a whole class is given on symmetry, and I'm just going to try to condense that to 2 days, which is a little ridiculous. But some of the words, if you go on to chemistry, no matter what you do, even if you're a synthetic chemist, you'll hear these words spoken of quite often. So you'll get some exposure. If you weren't destined to become a chemist, but I don't know why you're here anyway. So, so you're going to have to take it anyway, all right? Let's see, we'll start grading the test tomorrow. I have no idea how you did. I haven't looked at any of them yet. I was busy with other stuff, so it kind of destroyed me last time grading them all myself. I just don't have that energy anymore. So anyway, we'll have them done by Wednesday. Friday is a gigantic review. That's me talking 2 straight hours. It's pretty rough, actually. So I'm going to cover everything we covered in this class, and as usual, draw hints. And one of you was right. The final is Monday at 8, so I'll update the calendar. Monday, 8 o'clock in here. 2 hours. That sucks, but I don't know. That's what they gave me. So trust me, I don't like that at all. Anyway, maybe over donuts or something. So
is that going to be AM or PM?
8 p.m. 8 a.m. 8 a.m. for this class. I'll send a reminder email out. So and also I was late putting up the test 3 answer key. I didn't realize I hadn't done it, so I just posted that. And I don't think I have anything else. Do you guys? Anybody have questions about anything? You're set. All right. So again, I'm gonna go on a limb here, guessing you've all forgotten the symmetry stuff. Right? Okay. I'll go over what I only got to about 1 page of notes last time anyway, so I'll just go over it kind of quickly, and then maybe walk from there. Let me motivate you though about why are you doing any of this? Again, it's kind of this PChem 3 technical material. It's because it turns out that this is relevant for PChem 2, the quantum mechanics, because a lot of quantum mechanics, when you do the calculations, you're going to calculate, you're either going to 0 or 1. And that sounds, well, why did I bother? Well, it tells you a lot of stuff. 0 and 1 to me is very, very meaningful. Once you have to take the class, all right? It turns out that in terms of getting zeros, and that's often very meaningful, by the way. A 0 in quantum mechanics will tell you, like, no, it's not going to absorb light. And we observe everything through spectroscopy, right? Everything we know about this world is done spectroscopically. So that's kind of important to know when things absorb and don't absorb light and why. And that's a 0 in quantum mechanics. It turns out you can use this symmetry stuff to figure out a 0 ahead of time without doing any math whatsoever. And like I say, it's about half the time you're going to get a 0. So half the time, with symmetry on your side, you don't actually have to do the problem to begin with. Right? And this is kind of like when you're integrating even versus odd. Even, you're going to have to integrate it because it's going to come out to be something, and odd, you don't bother, it's automatically 0. So that's kind of like this, except it's, and obviously it gets more complicated. And this works because the Schrödinger equation, that's about the first thing you're going to cover in 346, probably within the first week. The Schrödinger equation contains the symmetry of the molecule, and the answers to the Schrödinger equation have the symmetry elements of that molecule. And that also dictates whether there's degeneracy, right? Now remember, hydrogen, so you're going to cover hydrogen atom. There's a 1s orbital, there's only one, that's non-degenerate. There's 2 p orbitals, a px, py, pz, 3 degeneracies. These, there's 5 degeneracies. Why? Because atoms are round. That's the kind of thing that I'm going to cover right now. Now, in 346, you're probably not going to hear that, but that is the ultimate answer for why hydrogens have these degeneracies. It's because it's round. And as soon as it becomes unround by bonding to something, that slowly goes away. If it bonds to another hydrogen atom, H2, it still has a lot of degeneracies, but they're not as many. If it bonds to a carbon, and carbon has other atoms, and it's losing symmetry as a result, because, you know, a sphere is perfectly symmetric. That's the definition of perfection and symmetry. Anything that causes that to get chipped away at till it's gone costs you degeneracies. So that's why. It's a good thing to know about. So why that ultimately happens. Okay, let me cover what we went over last time. I'm going to do this part quick. I've gone over it once. What we start with are symmetry operations. And then, inversion, rotation, right? I can rotate water, I can rotate it 180 degrees and that looks the same. All right, then what we do, once I defined most of the operations last time, let me breeze through that again. And then what you do is you apply them to molecules and see whether they look the same after they've been rotated or inverted or whatever. And depending on how many of these operations you have, defines its point group. Its point group defines its symmetry, and these zeros or ones in quantum mechanics. So let me remind you, so we have three operations. And I'll put one question on the test. And we can also sometimes think about things having local symmetry. I can tell you that there's C4D local symmetry, but ligands may technically break that. But that was just an example. I won't get into this too much, but anyway. So I can see that, like, I can cut this not two different ways. It looks like I can chop it this way and this way, but I can also chop it that way, and chop it that way. I can it's like an egg, and I have a, what do you call one of those things? Frying pan? You know, but the thing you use the frying pan, the little scooper deal. Spatula. Down to Spatula City. So I can spatularize it, like an egg muffin, I can just slice it in two. So anyway, just an example. Remember, E was do nothing. That's actually really important. E has a lot to do with rotational symmetry. Why have something that does nothing? It's actually about the most important operation that exists, even though it's not an operation. Okay, so now it's weird. The sigma is a plane of symmetry. And that was easy. So these are sigma planes. Better yet, OH. Again, I did this last time. OH, H2O. I got this guy here. Again, that's my spatula, cutting it in two. And then I can cut across the space. Like that. Okay, so I see two planes of symmetry. So that's pretty easy. And there's different types. Like this one here in the board, that's a vertical plane because it goes right through the molecule. This one that cuts it in two, I can't, I have to admit, I think that's a horizontal type, and I'll get into that more often. And that's the only thing that matters is that it cuts, whenever a plane cuts cuts a molecule in two, bisects bonds, like bisecting the HOH bonds, then that's when it's a horizontal plane.
Yeah, they're both vertical.
No, vertical is this one, in the plane. The one coming out of the plane is horizontal.
No, that's be horizontal if it's perpendicular to the C2 axis.
Perpendicular, oh, that's horizontal, perpendicular. And then this is a dihedral. This is a dihedral then, right?
The one.
Yeah, sorry,
you can
sorry.
use Sigma D.
Yeah, sorry, but that means that we're organic within God, so. Let me also move in, I think most of you haven't had inorganic, that's what I've heard, and so this is a big part of inorganic. Sorry, so yeah, this is the vertical, I got that one right. And then this one is the dihedral that cuts in two. In a horizontal, this doesn't have horizontal symmetry. I'll show an example of horizontal type of airplanes. Thanks for catching me there. I don't want to screw up your organic. And let's see, now I've got CN, which is rotation. Okay, and N means the angle by which you can rotate something. And it gets what it looks like itself. In this case, I've got, here I have to draw it going downward because I'm running out of room. I've clearly got a C2. Right, and that means that I can rotate this by 2 pi over 2, which is pi, which is 180 degrees. And it basically looks the same. And anyway, this tends to come up a lot. Here's an example of a C3. Boron, boron trifluoride. Obviously, if I do one C3 rotation, that's 3 into 180, 60 degrees, right? I think, yeah, 60 degrees. And so that's F1, F2, F3. So anyway, and you can get as high as, like benzene. That's one of the higher rotations that has a C6 rotation, right? That's kind of obvious. Let me also show where you have multiples. Let's take a C4. So this is all stuff about rotation. All right, you can do a C4 4 times. I mentioned this last time. C4 4 times. You can do it twice, 3 times, 4 times, whatever. And what's important about that is that that's the same as doing nothing. That's equivalent to E. And again, this is going to come up. The way these things multiply, technically I'm doing C4 times C4 times C4 times C4, C4 to the 4th power. That's exactly the same thing. And the way these things multiply times each other turns out to be really important. I'm just letting you know that that's the case. Excuse me. Now you'll also have inversions. Let's see, if you do, take like C3, C4 3, that's like a backward C4, right? So it's like, going 3 times around is the same way of going once around, just left hand instead of right hand. Okay, now that's important because if I do this, if I do C4 3, and then I follow up with a C4, then I've got an E, and therefore, the inverse of C4 is C3. Okay, so as in all things. Anyway, let me go ahead and again preview how you want to start thinking. Think in terms of matrices. You can invert a matrix. And then when you multiply a matrix times its inverse, you get the identity matrix where all the diagonals are 1 and everything else is 0. Just kind of keep that in your head. Because I'm going to eventually turn all symmetry operators into matrices. And again, it's hard to see why, but we're getting there. Okay, so this is all the things about C3, CNs. I have I, which is an inversion. And the example I gave before. So you can see why this is going to be very important in inorganic, because inorganic molecules have lots and lots of shapes. And the way you think of how their electrons work is actually dictated by, what are we going to do? 1, 2, 3, 4, This is the 5 and 6. And then if I invert, then I've got this. Oops, sorry, handwriting's not good today. So what's important about this guy, here, let me just draw it, sorry, I usually don't like to write in awkward silence, but option. So you're going to actually cover a lot of quantum mechanics in organic because you can understand so much about the electronic structure of these things based on their shape. Because the Schrodinger equation, again, takes the shape of the molecule itself. 3, 4, I know this is a little childish, yeah, I know, but here you go. Anyway, so everything got inverted. In terms of a matrix, what I see here is that every element of x and y and z, if I wanted to write the coordinates out, has picked up a minus sign. All x's and y's and z's that define the Cartesian coordinates have been minus. So that's I. And then S was the last one I got to, which is an improper rotation. And this is a weird one. This is two symmetry elements, two other symmetry elements combined. And what this is oh god, this is really painful. Oh, sorry, I should say S to the n. Sorry, S to the n. My bad. And so this is a rotation. Followed by rotation next, reflection, perpendicular, I'm going to use the symbol for perpendicular like you're used to. I don't know if I'm spelling that right. I don't think I am, whatever. So you reflect perpendicular to that. In the example I gave last time, here, let me just erase this, because this is stupid, I think this is like alanine. I don't quite remember. Can't remember the name of it. I'm pretty sure it's alanine. And, oh God, I don't make wrong this. Oh, that looks awful. Anyway, all right, so this guy's coming out. And, sorry, let me just try to get it kind of in my head what it looks like. And this guy is coming up. And this guy is down. And so the first thing we'll do is rotate. So this is this is an S4 rotation, meaning I'm going to do a C4 rotation first. Oh God, sorry. I'm going to have to right. Left to right, right to left. Okay, so then this guy is up. This goes down. Anyway, you kind of have to put this in your head because unfortunately, the bane of all stereochemistry is that it has to be done on a two-dimensional board. And then if I do the last operation, there's other operations, but these are the important ones. Now I reflect across the mirror plane and I end up coming right back home. And again, you kind of have to put this in your head to see what's happening. Or what I often see is somebody will take an image and then they kind of try to change the angle that you're looking at it. It kind of helps. But I don't believe it was a true three-dimensional television set with television glasses. I mean, I don't see how it's technically possible not to have those little glasses on. You've ever seen 3 dimensions? Let's see. Okay, so those are symmetry operations. And I think there's two more, but I just let's forget about them. I can kind of selectively choose which subsets of these things to show. Okay, now again, the point of the game is you apply these operations to a molecule, you see how many you've got, and based on how many you've got and what they are, you don't have to worry about ordering or anything like that, then you decide its point group. Okay, so point groups. Now you can imagine, think about your organic and how many crazy ways you could make carbon atoms twist and turn. So there's about 20 point groups. So I'll go over some of them, not all, because it's too much. I don't even know if Neil goes over all of them. He probably does. Okay, now, You can imagine, I take like a protein. While it may be like my iron guy friend up there and have local symmetry, like how every carbon sits in a tetrahedron, the reality is there's no way a protein is going to have one of these symmetry elements work perfectly across the entire gigantic globular mess. Okay, in that case, you have a C1 plane. And I think I have an example. Yeah, this guy. All right, other than proteins, which you can imagine, you're not going to reflect across any plane. Now remember that nitrogen has these lone layers that cause it to sit like an umbrella. And so you can make this guy here. Now, I can't, sorry. Fluorine. Apparently this is a thing. I can't bisect it, I can't rotate it. I can rotate it 360, but that just doesn't count because that's an E. So anyway, now the good thing about no symmetry, as I alluded to before, no degeneracies. That actually is kind of useful because here's the thing. Knowing that you're in a situation where degeneracy exists and you're actually trying to do quantum mechanical calculations, you've got a problem. That is going to be a very, very difficult molecule to work with to do the quantum mechanics because the degeneracies can hide themselves. So you've solved the Schrodinger equation, but you've got a degeneracy. You have to know it's there. And then there's tricks to tease out the other state. So in other words, I'm doing a calculation on hydrogen. And, you're being graded on it, maybe. I don't think that's going to happen. All right, but if you're not careful and you're solving wave functions on a computer, it'll come up with your 1s, and then it'll come up with a 2s, but it'll come up with a 1p, like a px, but it'll stop there. It won't find a px, py, or pz, because it thinks it's done. And again, we solve wave functions with computers. I mean, you're going to solve it for hydrogen atom, but once you get more than one electron, which is basically everything but hydrogen, you cannot solve it doing this. You have to solve it on a computer. And again, the computers are blind to degeneracies, so you've got to know that. So whenever I was doing calculations, I used to do this in grad school. If you go on to PChem in grad school, you will be doing this at some point. You've got to know the degeneracies there ahead of time. So it's a real pain in the ass, but we got C1 symmetry, you never have to worry about it. Lots of things are C1. Okay, then we got CS, also a friend. That is a one reflection plane. Excuse me, those are going nuts today. Now, don't hold me to this, but I believe CS also has no degeneracies. After this, they start having degeneracies. And again, I'll show you how you know that, other than I just told you. Okay, if I'm looking at this particular form of, it looks like formaldehyde, but it's chloroformaldehyde, which is probably incredibly toxic, I would imagine. I want to try to cut it and, chop it in two this way, but I can't. And so I don't see this. Anyone see the symmetry plane?
Board.
Yeah, it's within the board. So I haven't tried to draw it like this. Right? I'm trying to draw it like this. It's actually inside the board. It can be cut in two. And wait for this. This is going to come up in a minute. This is kind of a pain in the ass. You're like, well, that doesn't really do anything. Well, right. I mean, that's when you have a valid symmetry element when it doesn't really do anything. But at the same time, it kind of does. So that's where this gets a little tricky. Now, think of this as atoms having real volume, not just lines on a board, right? So I'm just thinking about if I can kind of squash myself inside the board here and hold on to the oxygen, there's a back half and a front half. And this reflection plane takes that back half and makes it the front half and vice versa. So that's why it's just important to recall that because it's going to come up in a minute. Okay, CI equals center of inversion. Center of inversion. And let's see. Okay, here's my example of that one. And let me tell you, so all these guys have something really interesting about them, like how C1 is no degeneracy. Again, I always like to do calculations of C1s. I wasn't always smart enough to figure out. I was never quite smart enough to tease out degeneracies. And then make sure I'm doing this right. Yeah. And unfortunately, again, you kind of just have to imagine that if I had a point right in the center, and then I project through, God, I hate drawing three-dimensional things on two dimensions. This hydrogen is kind of sticking out, so if it goes through the bond, it's going to end up on the other side. So there you go. Also, again, when I start doing matrices, every XYZ coordinate has a minus sign in front of it now. And that's how it got flipped. Okay, then we got CN. So notice that there's overlap between a lot of these names and the symmetry elements that comprise the name. It's not perfect. So as you can see here, these aren't operations, right? This one is an operation. It just kind of comes and goes. Here's the unfold axis of rotation. Okay, now you're picking up the genesis in terms of electronic structure. Now you've got it's nice and elegant, that it's symmetric, nice to look at the same time. Pain in the ass. Here's an example of C3. And so we've already gotten used to this. I think this is boronic acid. And anyway, it's kind of interesting because it sticks out a little bit. Because remember, oxygen has those lone pairs, it's like little rabbit ears. That's why it does this. Okay, I give an example of the C3 group. And now another thing, I don't think I emphasized this enough yet. The thing is that that's all it has, right? I can't slice it to the middle. I don't see a plane where it wants to reflect. I don't see an improper rotation. All it can do is be turned three ways, and then that's it. There's no other operation. So once I figure that out about the molecule, I say that is the C3. This molecule belongs to the C3 group. Okay, now let me do something very important here. Now, I know this may not seem super meaningful now, but I'm getting there. And that is multiplication. I can look at this molecule and come up with this multiplication table. Let me explain what that means. So this will be the C3 multiplication group. So I'll put that in the corner of the matrix. Now, I can see that it has a threefold axis of symmetry, but there's other things I can do to it. Technically I can operate up on an E, just to do nothing. Again, actually really important to include that. That one's in everyone. I can certainly do a C3 rotation. I mean, that's the point that it's in this, I think this is boronic acid. And I can also do it twice. What about C3-3? Yeah, it's already up there. Right, exactly. Okay, now the way to read this, this is your first operation, this is your next operation. And of course they're symmetric. Wouldn't make sense otherwise. And E's pretty much always return exactly, since E is do nothing, that makes the up and down are identical. C3, C3. Okay, so that's easy. Next one. C3 followed by another C3 is? C3 yeah. That was easy. Let's see. Now this is kind of interesting. The E's, C3 followed by C3 squared. Right, that's an E. Right? That's a C3-3. So that's it, and of course it's symmetric. Okay, C3 squared by C3 squared is? Yeah, exactly. See, this stuff is easy. And so you can imagine, this is why we're upset that we're not filling in 4, 4, 4. This is as hard as 4, 4, 4 gets. Have I done any integrals? The point, again, is to not do the math and to use shape to find those zeros, which is incredibly useful. So, and I'll do a couple more. Let me do another point. Actually, I meant to point out, again, why does this garbage matter? I should call it garbage. Because take like CI. If you're in the CI twin group, you're not Raman active. So Raman spectroscopy, right? It's kind of the same thing as infrared spectroscopy, except that it uses scattered light. By scattered light, I mean, when you see a laser beam, you're on PChem lab, right? We intentionally inserted 3 labs with lasers because lasers are fun. All right, but you know an eternal laser, you've seen videos, you've seen movies, you can see the beam, right? Come on, you can see the beam, right? Anyone know why? What was that? Yeah, dust. If there's no dust, can't see the beam. Right, so that's technically scattered radiation, and molecules do it too. So you can technically see the beam, but molecules scatter light weakly. It means that the light bounced off of it, literally, it just bounced off of it. It didn't get absorbed when we emitted, that's fluorescence. It just bounces off the molecules, but it's a very weak effect. So what happens is that sometimes the interaction of the laser light, you need a laser because again, it's a very weak effect. The laser bounces off with a different frequency, which was caused by absorption, by a vibration. But if you have this point symmetry, if you're in the CI point group, it doesn't do that, and your Raman spectrometer is now useless. So again, little factoids about symmetry, and it's very important in spectroscopy, because spectroscopy is the Schrödinger equation. Okay, CNV. Okay, so I know that there's a CN axis. Okay, but now I'm finding that this molecule has more symmetry elements. If it has more symmetry elements than CN, then it's now in a different point group. And in this case, the extra one, N collinear, sorry, it's important to put collinear, not linear, collinear with rotation, thin collinear planes, mirror planes, I'll just say planes, that are collinear with the rotation axis. Okay, and so that's water, because, let me show that again. Obviously now I can do a little bit better. Here's my C2 axis of rotation, but, okay, and so I need to find two planes that are going to lie along that rotational axis, and I've already done it, and this is childishly easy. Here it is. And they get different designations. I even brought that up before. Sorry, I'm trying this right. Different designations, because obviously this one in the plane is kind of more important. It gets this designation. This guy, being a baddie, trying to cut it in two, gets a little prime. That's how, it's just a stupid way to distinguish. It doesn't really actually matter that much. Okay, now, imagine doing this one to make a multiplication table. So, and it turns out that, so you see 2D multiplication table. So now we've got to think about all the operations that can occur within this limited point group. And why does this matter? Because this is actually the part where I'm doing quantum mechanics. You don't see it yet, but you will. Okay, I know I can do E, that's E's and everything, C2, and I already mentioned that there's two mirror planes. Okay, and of course it's symmetric. There you go, it has to be symmetric. So I won't have you do all of them. Let's do the easy ones. I'll point out one or two examples. So you can see that it's, you know, it does make things a lot easier, but at the same time, you do have to sometimes put some real thought into generating these things. And okay, E's are always easy. E, C2, C. And, I'm sorry, let's put E down C2. Okay, so let me just fill them all out. C2 by C2, okay, that one's easy. Go forward, go backward in terms of mirror symmetry, and then the same thing. So those are identical. Okay, let me just do two examples, and it shows you how you really got to think about this sucker. It's really tricky, and it's kind of fun. I mean, you can either have fun solving equations, or you can have fun looking at shapes of molecules. So I kind of like, it's like it takes all the math, and instead of being a mathematical hard thing, it becomes a crossword type of hard. But let me make sure I get it right. Let's do this one. Okay. So, all right, here's my issue. if I rotate it, so yeah, let's permute labels. This is 1 and this is 2 now this is 1 and that's 2. All right, and then this mirror plane wouldn't really do anything, right? You know, so I've taken it, I've rearranged it, and then I've, made it, go inward and outward again, kind of collapsed and re-expanded. Now that looks to me like this did nothing. And therefore, this operation is C2, because that 1, 2 is now 1, 2. It's flipped sides. It's not C2. Okay, it's actually, let me make sure I get it right, it's actually sigma V prime. Okay, now why is it sigma V prime? Now sigma V prime, I can see that it turns the 1 to a 2. All right, sorry, 1, 2 to 2, 1. I can see it does, it looks like it does the same thing, but not quite. It's really subtle. Again, I want to insert myself into the board, and now I'm holding onto the hydrogen atom. There's a front and there's a back. Now when I do C2, that back is now a front, right? This used to be the front, now it's the back. So that's changed. And so then the sigma V then, switches sides. So now the front remained the front. But that is actually exactly this operation. Because in this operation, it's done this, right? So that's why it's not C2, because C2 turns the front to the back, but the sigma V does not. It still switches them, but it doesn't permute back to front. So again, that's why these are really kind of subtle. And it does require you to really sit there and think about that kind of stuff. And there's different topological ways of doing it. I've got all the time. And, let me just finish it out. And what I could do on the test, I'm not sure yet. I haven't written the test. I could do something like have point a character table and then say explain an entry, or maybe come up with an entry if I think it's easy. I won't really get anything too hard. So if you're interested, you can look at this guy and just think about this molecule and why these operations come out the way that they do, and I can put it on the test, something like that. But damn, I can't believe we're out of time, so I want to give your homeworks back. And anyway, we'll finish this up next time.
Really? So I can get, my base was working out, I ended up getting charged with much overtime.